In this module, we will move on to talking about intermolecular forces. So I will enunciate here, it is intermolecular, not intramolecular. So intermolecular forces, these are much weaker than bonding forces. The bonding forces, so something like a covalent bond, an ionic bond, would be intramolecular. It's inside the molecule. These are forces between two molecules. They're weaker because they occur over longer distances, and they originate from interactions between charges, partial charges, and or temporary charges that exist on molecules. We'll look at the different types of intermolecular forces, and I very often abbreviate this as IMFs. So London dispersion forces, or van der Waals forces, you'll see these two names used interchangeably. These are present in all types of molecules. So every single molecule in existence will have London dispersion forces as an intermolecular force between molecules in a sample. These are the weakest, and they are an attraction between an instantaneous dipole and an induced dipole on neighboring atoms. And of course, I'll draw you a picture of this in a second. The magnitude of these forces depends on how easily the electron cloud around a molecule can polarize. Now, polarizability, you can kind of think of it like squishiness. So, right, we have all of these electrons that are around the nucleus in an atom. The bigger that electron cloud is, or especially the bigger it is, the farther from the nucleus some of those outer electrons are. It's a lot easier to kind of squish that electron cloud around, in part because of a little bit of the effective nuclear charge. But right, the attraction between the electron and the nucleus has a really far distance, and all of those electrons are moving the entire time. We don't know a lot about their location because we've really sacrificed that to have energy information, if you remember quantum mechanics. But right, they're moving all around. It's always possible that it's not a perfect sphere. So what that looks like in terms of a picture, if I have my normal electron cloud, right, I've got some atom, my electrons are moving around outside it. At some given point in time, all of those electrons could be squished over to one side more so than the other. This would give an instantaneous dipole. So the side that the electrons are all kind of squished toward, that has, you could think of it as having extra negative charges, that has a partial negative charge on that end, which means the side or the end of the atom that the electrons have kind of instantaneously vacated has a partial positive charge. Now, that instantaneous, randomly, electrons are in a spot that has this with an unbalanced charge. It will induce a dipole in the molecule next to it, or in the atom or molecule next to it. I guess it depends on the sample. So that all of those electrons squished over to one side, creating a partial negative charge, will repel electrons on the appropriate side of the molecule that's next to it. So that induces a partial positive, and then all of the electrons get squished over and creates a partial negative. Now you have a partial negative and a partial positive that can attract each other. So this is an intermolecular force. It's between two molecules, or even two atoms, really, but between things in a sample that are not bonded to each other. We can look at trends with all of these, and we will. So something that London dispersion or van der Waals forces are good for showing a trend for are boiling points for the noble gases. So we're going to look at boiling points, noble gases, helium, neon, argon, krypton, xenon. So that's from smallest to largest, right? We're just going down a column in the periodic table. So adding a shell of electrons every time we go to the next the next element. The boiling point for helium is 4.2 Kelvin. So really, really cold because we're really in Kelvin. So 4.2 Kelvin. Neon, a little bit bigger. That means the strength of the intermolecular force is stronger. The boiling point is 27. If we jump to krypton, we have a boiling point of 120, xenon 165. So what's happening is that as the atom gets larger, it gets more polarizable. It means that the temporary and the partial charge, the temporary slash partial charge, is a larger magnitude. This results in a stronger attraction between those molecules. And to boil a sample, you have to overcome that attraction. That's the interaction that we're breaking when we take something from a liquid to a gas. So it results in a higher boiling point because we have to break a stronger force in order to boil the sample. There are exceptions to this, and it's still the same intermolecular force. We just have to remember all of the things that are going into how these molecules are shaped. So we're going to look at pentane as an example because there are different ways that the carbons and hydrogens in pentane can connect to each other that give different shapes to the overall molecule. So N-pentane, and then we're going to compare it to neopentane. So both have molar mass of 72.15 grams per mole because they both have the same number of carbons and hydrogens. N-pentane has a boiling point of 36 degrees Celsius. Neopentane has a boiling point of 9.5 degrees Celsius, so much lower than for N-pentane. So what these structures look like, N-pentane is just the carbons are all connected in a long chain, and then, right, I've just filled in hydrogens for all of the other available bonding spots that carbon likes to fill up. Carbon loves having 4 bonds. So I have this long string of carbon atoms with hydrogens attached. Neopentane has a carbon in the middle. That carbon is connected to 4 carbons, and then those carbons are all connected to 3 hydrogens. So same number of each type of element, hence the same molar mass, but the shape is very, very different. I've got kind of like a long, I don't know, almost M-shaped molecule on the left with N-pentane, and I pretty much have a sphere with the neopentane. If we're looking at, now I'm going to tell you, now this doesn't have other intermolecular forces that we have to worry about. You'll be able to discern that in a little bit once we talk about them. This has London dispersion or van der Waals forces as the thing that we have to worry about here. So, I mean, polarizability, probably about the same. It's the same electronegativities of the atoms. It's the same number of electrons all put together, but the shape is very different. So if we kind of take the atoms out and just draw the interactions, like where the intermolecular force interactions would be. So on my electron cloud gets squished around, it induces dipoles in another molecule, you have that attraction. For the N-pentane, you can have this really large area of interaction and different places, points of attraction with the intermolecular force. For the neopentane, I mean, it's a sphere. You really just have like whichever one side has the partial charge to interact with the induced charge on another molecule. So they have very different areas for interaction. So what this results in is that it's just a lot harder to pull apart the N-pentane molecules to get them to boil. So we have to put in more energy. So we have to heat it to a higher temperature. So this is all, I kind of like to think of the N-pentane as like pulling apart pieces of Velcro, right? a long piece of Velcro, you have to put more force in it to tear it apart than if you had little tiny pieces of Velcro. The second intermolecular force and the next strongest, I mean, we started with the weakest, so the next strongest intermolecular force are dipole-dipole forces. These exist in all polar molecules, or really all molecules that have a dipole moment. And now it's a permanent partial positive on one molecule attracted to a permanent partial negative on another. The strength for this depends on the magnitude of the dipole. So I have hydrochloric acid here as an example, right? Hydrogen, chlorine, they have a pretty big difference in electronegativity. I think they have a difference of like 1 or 1.1. So we have a permanent dipole for the molecule that matches the bond to dipole. So I've got partial positive on hydrogen, partial negative on chlorine, and I've drawn my vector in here to show that this has a permanent dipole. The attractive force is between the negative end of the dipole and the positive end of the dipole. So this is how these would be attracted to each other. The next intermolecular force is hydrogen bonding, and this is the strongest intermolecular force. It is a strong enough intermolecular force that sometimes when hydrogen bonding is talked about in biology, it's referred to as the weakest bond. That's because it's being compared to things like covalent and ionic bonds, those intramolecular forces. This is an intermolecular force. So between two different molecules and out of London dispersion or van der Waals and dipole-dipole and hydrogen bonding is the strongest. It exists in polar molecules, but in very specific ones. It only exists where a hydrogen atom is directly bonded to a small electronegative atom. So hydrogen must be connected to nitrogen, oxygen, fluorine, or chlorine. The result is that it's just a much stronger partial positive and partial negative. So the way that I have this drawn here, your hydrogen bonding must be drawn this way, and if you draw other intermolecular forces this way, it would be incorrect because this is only for drawing hydrogen bonding. So water has hydrogen bonding. The hydrogen bonding is responsible for a lot of the weird properties that water has compared to other solvents and other similarly structured things. The oxygen has the partial negative, the hydrogen has the partial positive. The hydrogen bond is specifically the interaction between that hydrogen with the partial positive and one of the lone pairs of electrons on the oxygen of another molecule. So hydrogen has to be connected to nitrogen, oxygen, fluorine, or chlorine, and then that hydrogen has to interact with the lone pair on one of those atoms on another molecule. So we're doing pure substances, but if I had a mixture of ammonia, so NH3 and H2O, both of those things are capable of hydrogen bonding. You could have hydrogen bonding between those two. But we're going to stick with pure samples because we're really using this to talk about properties of samples of a compound. There is one more intermolecular force that I want to mention, and it's not, right, hydrogen bonding was the strongest. So the first three, those are the intermolecular forces that we see in pure samples. So you will see it in the pure sample of a substance. It's possible to see it in a mixture, but you can see them in pure substances. This last one would only occur in a mixture. So you will not have this for a pure sample. You can only have ion dipole forces in a mixture. And this is part of what helps ionic compounds dissolve. We'll talk about the energetics of that a little bit later. But ion dipole forces, this is the interaction with the ion from the ionic compound when it splits up in solution and the dipole of the solvent. So this is going to, I think we have this coming up in a little bit. This is going to contribute to why some things dissolve in water and why some things don't. There are other factors that go into it, but if you want something like Na plus to be happy in solution, having it surrounded by negative charges, it's going to kind of feel like it's still in its lattice, except now it gets to move around a lot. So this is a picture of what an ion dipole force would look like. I've got my ions here in the solution, my Na plus and Cl minus, and then the water molecules that are surrounding it, which being dissolved just means being surrounded by water molecules, they line up with their dipoles turned the appropriate way. So for sodium, since it's a positive charge, the negative end of the dipole would be pointed toward the sodium. For chlorine, the positive end of the dipole would be pointed toward chlorine.